Assalamualaikum and welcome to Linear Control System lecture. This lecture is a continuation from last section, first order systems. Let us now extend the concepts of poles and zeros and transient response to second order systems. Compared to the simplicity of a first order system, where varying a first order system parameter simply changes the speed of the response, changes in parameters of a second order system can change the form of the response. For example, a second order system can display characteristics much like a first order system, or depending on a component values, displays damped or pure oscillation for its transient response. The prototype of a second order system is given by Gs equals to omega n square over s square plus 2 zeta omega ns plus omega n square. From the characteristic equation of the system, we can find the poles, which is given by S1 or S2 is given as poles equals to negative zeta omega n plus minus j omega n square root of 1 minus zeta square, which we can simplify the term negative zeta omega n as negative sigma d and j omega n square root of 1 minus zeta square as j omega d. The poles can be represented on the S-plane. Now you can draw all the poles on the S-plane where the omega n is the distance between origin to the location of the poles. Zeta value can be found by taking the cos theta of the pole's location on the S-plane. Now, let me show you the root locus for a prototype of second order system where we fix the value of omega n and zeta is varied from 0 to infinity. Our scope of discussion only on the left-hand side of the S-plane, since the system will be unstable on the right-hand side of the S-plane. So we will not cover an unstable system. Let's get started where the poles are on the j omega axis. Say we have a step input, a plant Gs, and an output Ys. For example, Gs equals to 9 over s squared plus 9. When a pole exists at origin that comes from the unit step input and two imaginary poles on the positive and negative of the j omega axis that comes from the system, the input pole at origin generates a constant force response, and the two system poles on the imaginary axis generate a sinusoidal natural response whose frequency is equal to the location of imaginary poles. This type of response is called undamped. The absence of a real part in this pair corresponds to an exponential that does not decay over time. At this particular point, the value of zeta is 0. Next, let's consider the poles that are located between the imaginary and real axis. Say a function gs equals to 9 over s squared plus 2s plus 9. The function has a pole at the origin that comes from the unit step input and two complex poles that come from the system. We see that the real part of the pole matches the exponential decay frequency of the sinusoid's amplitude, while the imaginary part of the pole matches the frequency of the sinusoidal oscillation. The transient response consists of an exponentially decaying amplitude generated by real part of the system pole times a sinusoidal waveform generated by the imaginary part of the system pole. The time constant of the exponential decay is equal to the reciprocal of the real part of the system pole. The value of the imaginary part is the actual frequency of the sinusoid. This sinusoidal frequency is given the name damped frequency of oscillation omega d. Finally, the steady-state response of unit step was generated by the input pole located at the origin. A plot of this response appears for various values of zeta, plotted along a time axis normalized to the natural frequency. We now see the relationship between the value of zeta and the type of response obtained. The lower the value of zeta, the more oscillatory the response. The natural frequency is a time axis scale factor and does not affect the nature of the response other than to scale it in time. At this point of location, the value of zeta is greater than 0 and less than 1. We call this type of response is underdamped response. For a critically damped system, the value of zeta for this response is equal to 1. The function has a pole at the origin that comes from the unit step input and two multiple real poles that comes from the system. The input pole at the origin generates the constant force response, and the two poles on the real axis generate a natural response consisting of an exponential and an exponential multiplied by time, where the exponential frequency is equal to the location of the real poles. Critically damped responses are the fastest possible without the overshoot that is characteristic of the underdamped response. Finally, for an overdamped system, the zeta is greater than 1 and the poles is located on the real axis of the S-plane. Function has a pole at the origin that comes from the unit step input and two real poles that come from the system. The input pole at the origin generates the constant force response. Each of the two system poles on the real axis generates an exponential natural response whose exponential frequency is equal to the pole location. We see that the poles tell us the form of the response without the tedious calculation of the inverse Laplace transform. If you have any comment or questions, please leave me a message and I'll try to get back to you. Thanks for watching.